transformation begins quietly, almost unnoticeably, somewhere over the open ocean. A patch of warm water shimmers under the sun, and above it, moist air begins to rise slowly. There is no storm yet, just a subtle stirring in the sky. But this is how it starts. This is the beginning of something powerful, the process that turns invisible energy into a spiraling system of clouds, rain, and wind. What happens next depends on delicate timing, balance, and the right conditions aligning over thousands of kilometers of ocean. At this early stage, meteorologists call it a tropical disturbance. It's not a storm yet, but it has the potential to become one. This disturbance is usually a cluster of thunderstorms loosely organized in a wide area. You wouldn't think much of it if you were sailing through just some rain, maybe gusty winds. But satellites watching from space see more, a possible structure forming. The heat from the ocean continues to rise through evaporation, fueling the storm with latent heat energy. This energy rises, condenses into clouds, and releases heat back into the atmosphere, further fueling the system. It's a self-reinforcing cycle. Still, at this point, there is no closed circulation. The winds aren't spinning consistently. The pressure is still relatively high. But nature is preparing something. If the surrounding environment remains favorable, if the water stays warm, if the atmosphere stays moist, and if vertical wind shear remains low, this disturbance can begin to organize. The thunderstorms begin to cluster tighter. The winds near the surface begin to align and move inward, converging around a low-pressure area. The pressure drops. The clouds grow taller and thicker. The system becomes more symmetrical. You now have what's called a tropical depression. At this stage, things begin to change quickly. The central pressure keeps falling, and the winds start rotating in a more defined cyclonic pattern. The system is still not strong enough to be named a tropical storm, but it has reached a critical milestone. There is now a closed, low-level circulation. Air is spiraling inward and upward, feeding the storm. The clouds begin to wrap around the center. Rain bands develop. Lightning may flash within the core. What was once a patchy group of thunderstorms is now a baby cyclone taking its first breath. You might think this storm would quickly grow stronger, but that depends on its environment. If the wind shear increases or dry air invades the core, the system may collapse. Many tropical depressions die before they ever become named storms. But if the sea remains warm and the winds stay favorable, the depression can intensify. The rotation strengthens. The structure tightens. The rain bands expand. The pressure drops faster. The storm's engine is firing on all cylinders. Once the sustained winds reach 39 miles per hour, 63 kilometers per hour, the tropical depression is upgraded to a tropical storm, and it receives an official name. This is when public attention increases. Meteorologists begin issuing forecasts, models start predicting tracks, and emergency managers start watching closely. But make no mistake, the transition from tropical depression to tropical storm is one of the most critical stages in storm development. It's the moment the storm begins to assert its identity. It's no longer a maybe, it's now a growing threat. Tropical storms can vary widely in intensity and impact. Some stay weak, never becoming hurricanes. Others rapidly intensify, doubling their wind speed in a day. What determines that path? Again, it's all about energy. The more heat and moisture the storm can access, and the less disruption it faces, the faster and stronger it can grow. Warm sea surface temperatures act like jet fuel. Moist air provides the lift and condensation. Low wind shear keeps the structure intact. If all these factors remain, the storm begins to wrap tighter around its center. The eye begins to clear, the pressure falls rapidly, and a hurricane is born. But here's what many people don't realize. It's in this middle stage, between tropical disturbance and hurricane, where forecasting becomes the most challenging. A small change in ocean temperature, a sudden burst of dry air, or a shift in upper-level winds can drastically alter the storm's path or intensity. It's a fragile phase, yet one packed with explosive potential. At the same time, satellite data, buoys, aircraft reconnaissance, and computer models are all working together to track the storm's every move. Meteorologists analyze vorticity, sea surface anomalies, wind shear profiles, and pressure gradients. Every data point matters. Every update could mean the difference between a minimal storm and a catastrophic one. And yet, even with all our technology, storms sometimes surprise us, growing faster than expected, or turning in an unexpected direction. This is why early detection matters so much. The sooner a disturbance is identified, the more time communities have to prepare. And it all begins with understanding what's happening inside that patch of clouds over the ocean. The transition from a nameless disturbance to a tropical storm is not always dramatic, but it's always meaningful. It signals that the atmosphere is in motion, that the ocean is releasing energy, and that something larger may be coming. In the next chapter, we'll explore that transformation, the moment when a tropical storm strengthens, becomes a hurricane, and begins to take on a structure unlike anything else on Earth. You'll learn about the eye wall, the rain bands, and the terrifying beauty of nature's most organized chaos. If you're following this journey into the life of a storm, don't forget to subscribe to Crisis Lens for the next part. Every storm has a beginning, but what comes next is the real story. Stay tuned and stay prepared. Great. Here's part 1, 1300 of the long-form video script for Video 1. What conditions are needed for a storm to form? You asked for 3 hooks at the start, no headings, and engaging content suitable for both faceless narration and shorts. They don't appear out of nowhere, they don't erupt randomly like explosions, and yet when they arrive, they change everything. A storm, especially a tropical storm or hurricane, is not just wind and water. It's the result of a slow, invisible symphony of conditions aligning perfectly over time. And unless all 5 of these precise ingredients are present, there is no storm, only clouds drifting quietly across the ocean. Let's start at the very beginning. Imagine you're flying over a vast, quiet ocean. It looks peaceful, almost uneventful, but below that stillness lies something far more powerful: heat. The ocean's surface must be at least 26.5 degrees Celsius, or around 80 degrees Fahrenheit, and not just at the surface. This warmth needs to reach 50 meters deep or more. Why does that matter? Because warm water feeds storms. It evaporates into the air, turning into energy. Think of it as the fuel tank for any potential tropical storm. Without this heat reserve, the engine simply won't start. But warm water isn't enough on its own. You also need moisture in the air, lots of it. As that warm ocean water evaporates, it adds humidity to the air just above the sea. This rising, warm, wet air begins to form clouds. When enough of it accumulates and starts to spiral, you're seeing the early stages of a system that may become a storm. Without moisture, you've just got dry winds and sunshine. Nothing happens. So we have 2 ingredients, warm water and moist air. Now let's introduce the third element, something most people never think about: the rotation of the Earth, also known as the Coriolis effect. This invisible force is what causes the air to spin instead of just rising straight up. Without this spin, no matter how much heat or humidity is in place, a storm cannot organize into the tight, violent spiral we call a cyclone or hurricane. And here's something fascinating. Because the Coriolis effect is weakest at the equator, tropical storms cannot form right along the equator. That's why you'll never see a hurricane start at 0 degrees latitude. The Earth must provide just the right amount of spin. Too little and it fizzles, too much and it distorts. So we've got warm water, moisture in the air, and Earth's spin. But there's a fourth condition, one that acts like a hidden guardian in the sky: low vertical wind shear. That means there can't be strong winds blowing at different speeds or directions in the upper atmosphere. Why? Because those upper-level winds would tear apart the forming storm before it has a chance to grow. A developing storm is like a delicate sculpture of rising air. If the winds are too chaotic, it gets destroyed before it ever matures. So for a storm to form, the skies above must stay relatively calm, at least vertically. The fifth and final piece is often overlooked but absolutely essential: a small disturbance or trigger, some irregularity in the air to get things started. It could be a weak low-pressure system, a tropical wave, or leftover energy from another weather pattern. Think of it as the match that lights the fuse. All the other elements might be in place, but without this initial spark, nothing happens. It's like having a pile of firewood, gasoline, and oxygen, but no flame. The disturbance is that flame. Now picture this: the sea is warm, the air is wet and rising, the Earth is spinning gently beneath, the upper atmosphere is quiet, and there's a small trigger to start the process. That's when a storm begins to breathe. Not in a dramatic roar, but a soft, invisible exhale of energy. Tiny clouds gather, then more. They start to rotate, and soon a giant weather machine is born. But if even one of those 5 elements is missing, everything collapses. No matter how hot the ocean is, if the wind shear is too strong, the storm dies. Even with perfect rotation, if the water is cool or shallow, nothing happens. That's why most tropical storms form only in very specific zones of the world, between 5 degrees and 20 degrees latitude north and south of the equator, where all these factors quietly align. The beauty and terror of storms lie in this very precision. They are not accidents, they are not spontaneous. They are built piece by piece, layer by layer by nature itself. They are among the most complex and violent systems on Earth, and yet their formation is delicate, like a tightrope walker needing every element in balance. What makes this even more astonishing is how small the initial signs can be. A tiny patch of warm water in the middle of nowhere, a subtle shift in upper air pressure, a bit more moisture than usual. These tiny whispers in the atmosphere can evolve into monster hurricanes that wipe out entire cities, alter coastlines, and change history. And once that process begins, once a storm is born with all 5 of these elements intact, what happens next is even more extraordinary. It grows, it feeds itself, it spins faster, it becomes more organized, and soon it begins its journey, often toward land, where the real danger lies. That's what we'll explore in the next part, how that early storm transforms into a deadly cyclone, gaining strength as it goes. You'll see why monitoring ocean temperatures, air moisture, and even distant tropical waves is so important. Because the next great storm isn't born in chaos. It's born in quiet, in heat, in stillness. Before it screams, it whispers. If you found this breakdown fascinating and want to truly understand how storms develop, intensify, and eventually die, follow our channel Crisis Lens for the next parts of this series. We're diving deep into the science behind Earth's most powerful forces, with no drama, just truth. Subscribe now and stay updated, because understanding storms could one day save your life. Let me know when you're ready for part 2, how a tropical disturbance evolves into a storm, and I'll continue with the same structure. It begins to spin, slowly at first, almost lazily. The clouds wrap tighter, the wind picks up, and the central pressure keeps falling. What was once a loosely organized tropical storm now enters a new, terrifying phase of its life. This is the moment when a storm begins to transform into a hurricane. It's not a simple leap, it's a structured evolution, powered by heat, moisture, and an astonishingly efficient engine built entirely by nature. This part of the journey is when storms stop being just a curiosity on a weather map and become a real threat. As the storm strengthens, several things happen almost simultaneously. The air at the center continues to rise, drawing in more warm, moist air from the surface of the ocean. That air spirals inward, heats up, rises, and condenses into massive thunderclouds. This process releases latent heat, which accelerates the rising motion, causing more air to rush in at the surface, and so the feedback loop intensifies. It's nature's version of a self-charging battery. The more heat it gets, the stronger it becomes. Eventually, something remarkable forms: the eye. This is the iconic, calm center of the storm, often 20 to 40 kilometers wide, surrounded by the most intense part of the system, the eye wall. The eye is a direct result of centrifugal force. As the storm's winds spin faster, air in the center is flung outward, creating a low-pressure vacuum. In this zone, air sinks instead of rising, which suppresses cloud formation and creates the clear, calm conditions inside the eye. But don't be fooled. The presence of an eye doesn't mean it's safe. In fact, it means the storm has reached a new level of organization and strength. Surrounding the eye is the eye wall, where the storm's most violent winds and heaviest rains are located. This ring of thunderclouds spins with tremendous speed, often exceeding 120 miles per hour, 193 kilometers per hour in major hurricanes. The updrafts here are incredibly strong, forcing air thousands of meters into the atmosphere. Lightning flashes, torrential rain falls. It is a wall of chaos, hiding the eerie stillness at the center. As the storm strengthens further, rain bands spiral outward from the center, sometimes stretching hundreds of kilometers. These bands are made up of smaller thunderstorms, feeding the main system with energy and expanding the storm's impact area. Even if a hurricane never makes landfall, its rain bands can cause widespread flooding, high winds, and coastal storm surges far from the core. During this intensification, meteorologists constantly monitor a storm's central pressure and sustained wind speed. When winds exceed 74 mph, 119 km/h, the storm is officially classified as a hurricane in the Atlantic or Eastern Pacific, a typhoon in the Western Pacific, or a severe tropical cyclone in other regions. These different names describe the same powerful phenomenon, a rotating system fueled by ocean heat, governed by atmospheric dynamics and capable of massive destruction. What's most alarming is how quickly some storms intensify, known as rapid intensification. A storm can jump from a Category 1 hurricane to a Category 4 in less than 24 hours under the right conditions. This happens when ocean temperatures are exceptionally warm, the upper atmosphere remains undisturbed, and the moisture supply is abundant. Such storms leave little time for preparation, often overwhelming forecasting systems and emergency response plans. We've seen it happen before. Hurricane Michael in 2018, Hurricane Patricia in 2015, Hurricane Otis in 2023, all intensified rapidly, catching communities off guard. But not all storms follow a steady growth pattern. Some stall over the ocean, others weaken due to dry air intrusion or cooler sea temperatures. But when all the factors align, the storm strengthens methodically. It tightens, spins faster, becomes more symmetrical. It becomes a machine, a hurricane with an identity and a path. This is when people begin evacuating, when governments declare states of emergency, when news outlets issue non-stop updates, because the power of a hurricane doesn't lie only in its wind speed. It lies in the storm surge, the inland flooding, the relentless rainfall, and the psychological toll it exacts. To understand how deadly a hurricane can be, look at how organized it is. A well-structured hurricane with a defined eye and tight spiral bands is more dangerous than a disorganized system with scattered convection. That's why satellite images of hurricanes are so telling. Clear symmetry means maximum strength. The clouds swirl like a galaxy, each band feeding the core, each rotation pulling in more energy. And then something interesting happens, the eye wall replacement cycle. In very strong hurricanes, the inner eye wall can contract so tightly that it becomes unstable. A second, outer eye wall forms, cutting off the inner one's energy. As the inner eye wall collapses and the outer one takes over, the storm may temporarily weaken. But once the outer wall contracts and strengthens, the hurricane often rebounds stronger than before. This natural cycle can repeat multiple times and is one of the hardest parts of forecasting storm intensity. The height of the storm's power isn't always right before landfall. Some hurricanes peak over the ocean and weaken slightly before hitting land. Others do the opposite, intensifying right up until impact. Either way, once the winds exceed 157 mph, 252 km/h, the storm is classified as Category 5, the highest level on the Saffir-Simpson hurricane wind scale. At this point, catastrophic damage is expected. Homes will be leveled, trees uprooted, power grids destroyed, and yet, the storm may only be a few hundred kilometers across, proof that some of the most powerful forces in nature are tightly concentrated. The beauty of this process lies in its symmetry. It's a perfect engine. Warm water rises, releases heat, forms clouds, spins and grows. There's no waste, no chaos, just precision. Nature builds hurricanes with elegance and efficiency, and when they're done, they leave behind scars, both on the land and in memory. In the next part, we'll examine what happens when these hurricanes make landfall, how the interaction with terrain, cities, and colder ground environments causes storms to weaken, shift, or transform entirely. You'll learn why the damage doesn't stop after the winds die down, and why post-storm flooding is often deadlier than the storm itself. To keep following this eye-opening journey through the life cycle of a hurricane, don't forget to subscribe to Crisis Lens. We've still got more to uncover. How storms end, how they change landscapes, and how they teach us to listen to the language of the atmosphere. Follow now and stay with us for the next chapter. The moment a hurricane touches land, everything begins to change. What was once a finely tuned atmospheric engine fed by the warm ocean now begins to unravel. The storm that drew its strength from the sea must now face resistance. Dry ground, friction, mountains, cities, and cooler air. This moment, known as landfall, is often the most feared phase. It's when winds tear through homes, storm surges flood coastlines, and rain dumps relentlessly for hours or days. But landfall is not the end of the storm's journey. It's just a new chapter, one that brings a different kind of danger. As the hurricane's center crosses over land, the first thing that changes is its fuel source. No longer hovering over warm, moisture-rich waters, the storm begins to lose access to the evaporative heat it needs to maintain strength. Without that heat, the rising air slows down. The convection weakens, the core cools, the eye becomes clouded over. The tightly packed spiral structure begins to loosen. Within hours, wind speeds start to decline, but not before unleashing destruction on everything in their path. Then comes the storm surge, a wall of water pushed ashore by the hurricane's winds. This is often the deadliest part of a hurricane. Unlike rainfall, storm surge is immediate, forceful, and overwhelming. It doesn't rise gradually like a river. It crashes in, flooding roads, buildings, and neighborhoods in minutes. In flat coastal areas, even a modest storm surge can travel miles inland. Combined with high tide, the results can be catastrophic. Think of it as a temporary sea level rise. Except it's not gentle, and it comes with crashing waves and debris. While the coast takes the initial hit, the danger moves inland. Hurricanes carry immense volumes of rainfall, often more destructive than the wind. When the system slows down after landfall, it can stall over an area for days, dropping inches of rain per hour. Rivers swell, drainage systems overflow, roads disappear underwater, homes fill from the bottom up. And often, it's not just one day of rain, it's several, with the ground becoming so saturated that even small additional storms lead to landslides and flash floods. As the storm moves over hills or mountains, it encounters topographic lift, meaning the moist air is forced to rise even higher. This causes intense rainfall on the windward side of mountain ranges. In places like Central America, Southeast Asia, or even the Appalachian Mountains, this phenomenon has led to some of the most devastating post-landfall disasters in history. And yet, even as the winds weaken, the storm remains dangerous. Downed power lines, broken communication systems, impassable roads, these create secondary crises. Emergency responders struggle to move. Hospitals may lose power. Clean water becomes scarce. In developing regions, the aftermath of a hurricane often leads to a public health emergency long after the skies clear. It's not uncommon for hurricanes to transition into a post-tropical cyclone after landfall. The storm loses its tropical characteristics, but can still cause widespread wind and rain damage. Sometimes it merges with other weather systems and continues moving inland for hundreds or even thousands of miles. Hurricane Sandy, for example, became post-tropical before slamming into the northeastern U.S., yet its damage was historic. Because these transformed storms can still carry massive rain and wind fields, underestimating them can be fatal. One of the least understood aspects of landfall is the uneven distribution of damage. Most people expect the worst winds at the very center, but the right front quadrant of a hurricane, relative to its direction of motion, is usually where the most destruction occurs. This is where the winds combine with the storm's forward motion, increasing the effective wind speed. It's also where the storm surge is highest. People on this side of the storm face the full brunt of its power, often without understanding why. Another underestimated factor is tornado formation during landfall. The outer rain bands of a hurricane can spin off small tornadoes, especially in the right front quadrant. These are usually short-lived, but can still be deadly, especially when hidden in heavy rain. The chaos and noise of a hurricane often mask the signs of an incoming tornado, leaving little warning time. As the storm degrades further, it can still cause major flooding in areas far from the original point of impact. Think about Hurricane Harvey in 2017. After making landfall in Texas, it stalled and dropped over 60 inches of rain in some places. Or Hurricane Ida in 2021, which, after hitting Louisiana, brought tornadoes and deadly floods all the way to the northeastern U.S., including New York City. This illustrates a critical point. A storm's damage does not end at landfall. In many cases, that's only the beginning. Floodwaters can take weeks to recede. Infrastructure damage can take months to repair. Economies can take years to recover. and lives, displaced, disrupted, or lost, are changed forever. Even after the skies clear and the winds die down, the risk isn't over. Standing water becomes a breeding ground for mosquitoes and disease. Damaged power lines can spark fires. Looting and lawlessness may increase in areas where services collapse. And without access to clean water, food, or medical care, the true cost of the storm often becomes clear after the headlines fade. This is why disaster preparedness is not just about the storm itself, but about what comes next. Evacuation plans, emergency shelters, clean water reserves, and communication protocols can make the difference between survival and catastrophe. Communities that understand the full life cycle of a hurricane, from formation to landfall to post-storm impacts, are far more resilient when disaster strikes. In the next part, we'll follow what happens after the storm ends, how it breaks apart, how the energy disperses, and what long-term environmental and societal effects remain. You'll also learn how scientists are working to better predict not just storm paths, but their long-tail consequences. Make sure to follow Crisis Lens, and don't miss what comes next in this deep dive into how Earth's most powerful storms rise, rage, and fall. Stay informed, stay safe, and we'll see you in the next chapter. What happens after a storm ends? For many people, the instinct is to exhale, to believe the danger has passed, that life can return to normal. The winds have stopped, the rain has eased, the radar shows the system moving away. But the truth is far more complicated. Because when the storm's eye disappears and its winds die out, its legacy begins. The energy doesn't vanish. The destruction doesn't pause. In fact, for many communities, the most difficult chapter begins only after the last raindrop falls. After landfall, hurricanes often degrade into what's known as a post-tropical system. These systems no longer have the symmetrical, warm core structure of a true tropical cyclone. Instead, they take on characteristics of mid-latitude storms, merging with other systems, pulling in cold air, expanding in size. While the term post-tropical may sound harmless, these storms can still produce flooding, high winds, and even snowfall in certain regions. And because people associate weakening storms with fading danger, they're often underprepared. But let's move beyond meteorology and talk about the human aftermath. The silence after the storm can be unsettling. Streets are empty, trees lie broken, homes are shredded, power lines hang across flooded roads, and survivors, those who stayed or returned, are left navigating an alien landscape of loss and uncertainty. For days or weeks, basic services may not return. Hospitals are overwhelmed, gas is scarce, and in many places, communication is still down. Even more critical is the water, not the water that fell, but the water that lingers. Floodwaters don't recede quickly. They sit, they stagnate, they fill basements, seep into foundations, destroy furniture, rot walls, and they carry with them contaminants, sewage, chemicals, oil, dead animals. Walking through floodwater after a storm is not just risky, it's toxic. In many disasters, more people fall ill from post-storm infections than from the storm itself. Beyond the visible destruction lies an equally profound, often ignored toll: psychological trauma. The mental strain of losing everything, of being displaced, of fearing for loved ones. It doesn't disappear when the clouds part. Children have nightmares. Adults face depression, anxiety, and survivor's guilt. The community fabric is torn. Schools close. Businesses fail, and rebuilding feels impossible. Relief efforts help, but they can't heal everything. Some wounds are slow, invisible, and permanent. Then comes the question of recovery. Insurance claims take months, sometimes years. Government aid is slow, uneven, and often political. Rural areas get overlooked. Marginalized communities suffer more. And as national attention moves on to the next crisis, survivors feel forgotten. The storm may be gone, but the people it touched live with its fingerprints every single day. At the same time, the environment bears scars too. Coastal ecosystems are torn apart. Saltwater intrusion damages crops and freshwater supplies. Entire species are displaced. Coral reefs suffer from sediment and pollution runoff. And the carbon footprint of post-storm rebuilding adds to the same climate trends fueling stronger storms. It's a cycle, one that's accelerating. Scientists and disaster planners are increasingly focused on this tale of the storm, the long aftermath that doesn't make headlines but affects millions. They're studying how climate change is making storms linger longer, drop more rain, and cause bigger floods even after the winds fade. They're analyzing how infrastructure can be redesigned to withstand not just wind but water. Elevated homes, smarter stormwater systems, stronger levees. These are no longer optional. They are urgent. Even the way we forecast storms is changing. In the past, meteorologists focused on wind speed and category, but that's not enough. A slow-moving Category 1 hurricane can cause far more flooding than a fast-moving Category 4. That's why there's growing pressure to create new metrics that measure rainfall potential, flooding risk, and storm longevity, not just peak wind. And then there's the matter of memory. As time passes, communities forget, new residents move in, politicians shift priorities, but the people who lived through the storm remember. That's why community-based preparedness programs matter. Education saves lives. Drills, evacuation routes, emergency supplies, they seem tedious until you need them, and when you need them, they're everything. A storm doesn't truly end when it moves off the radar. It ends when the last family has rebuilt, when the last flood victim is safe, when the last traumatized child sleeps without fear. Until then, it lives on, quietly, powerfully, in the spaces we rebuild and the decisions we make. In our final chapter, we'll look at how the entire life cycle of a storm, from warm ocean to landfall to aftershock, shapes not just our coastlines but our societies. We'll explore how storms have changed history, redrawn maps, reshaped economies, and redefined how we relate to the planet. So don't stop here. Follow Crisis Lens to continue this journey into the heart of Earth's most powerful storms. The wind may die, but the story goes on. And if we listen closely, we'll be better prepared for whatever comes next. It all began with warm water and ended with broken cities. But the full life of a storm is far more than destruction. It is a process, a cycle, and in some ways a story. One that tells us about the planet we live on, the systems that govern our weather, and the delicate balance that sustains life or unleashes chaos. In this final chapter, we zoom out. We look beyond the storm's wind and rain to understand how hurricanes reshape not just the land, but human history, economies, and even the way we see our future. Throughout time, hurricanes have served as both natural disasters and turning points. The 1900 Galveston hurricane, the deadliest in U.S. history, killed over 8,000 people and changed how Americans thought about storm preparedness. Hurricane Katrina in 2005 didn't just flood New Orleans, it exposed deep racial, economic, and governmental failures. Hurricane Maria in 2017 devastated Puerto Rico and became a symbol of climate vulnerability and political neglect. These weren't just weather events, they were historical milestones that left lasting scars, both physical and cultural. But it's not just the biggest storms that matter. Countless smaller cyclones, tropical depressions, and unnamed storms have shaped coastlines, destroyed crops, altered river systems, and driven entire communities to migrate. In Bangladesh, Vietnam, the Philippines, and other vulnerable nations, storms dictate how people live, build, and move. And with climate change making storms wetter, slower, and more intense, the past is no longer a guide for what's to come. That's why understanding the full life cycle of a storm is more urgent than ever. When we know what creates them, warm ocean water, moist air, Earth's rotation, low wind shear, and an atmospheric trigger, we can better anticipate where and when they'll form. When we understand how they grow, from a tropical disturbance to a deadly cyclone, we can build better forecasting models. And when we grasp how they die and what they leave behind, we can shape smarter recovery plans and stronger infrastructure. This life cycle model is now being used to improve disaster risk management worldwide. Countries are adopting early warning systems, investing in resilient housing, and developing relocation plans for coastal areas. Cities are changing building codes, elevating structures, and reinforcing flood barriers. Emergency services are being trained for faster, more coordinated responses. And public education campaigns are helping communities prepare in advance, not just react in panic. The future of storm science is equally fascinating. Machine learning is now being used to predict intensity changes. High-resolution satellite imagery can map storm formation in real time. Drones and underwater sensors are being deployed into storm systems to gather data never before available. And as global temperatures rise, climate scientists are modeling how warming oceans and rising sea levels will reshape hurricane behavior over the coming decades. Some of these changes are already visible. The Atlantic hurricane season is starting earlier and ending later. Storms are forming closer to land, giving communities less time to prepare. Rainfall totals are increasing, making flooding a greater risk than wind in many storms. And the line between tropical and non-tropical systems is blurring, leading to more complex storm patterns that defy old rules. This is not fear-mongering, it's reality. But it's also a call to action, because we are not powerless. The more we understand storms, the more we can adapt. We can change how we build, how we plan, how we prepare. We can fund science, prioritize safety, and protect the vulnerable. Nature will always do what it does, but our choices decide the outcome. And that's the final truth of the storm story. It's not just about weather, it's about humanity, about how we respond to crisis, how we rebuild, how we learn, and whether we have the wisdom to listen to the planet as it speaks through wind and water. So, if this series helped you see storms differently, not just as terrifying forces, but as living systems with lessons to teach, then stay with us. Follow Crisis Lens for more deep, evidence-based storytelling about the forces shaping our world, because this storm may be over, but the next one is already forming. And the more we understand, the more we survive. Subscribe now and explore what nature is truly capable of, and how we can prepare for what comes next.